Welcome to Chapter 2, where we're going to start working with rates of change. So let's, before we jump into 2.1, just briefly discuss the difference between these two terms. What do we know about speed and velocity? Speed tells you how fast you're traveling, right? Now, what's handy about velocity is it also tells you how fast you're traveling. But you might remember from physics, for example, when you're talking about vectors, where velocity doesn't just tell you the rate at which you're traveling, it also tells you the direction in which you're traveling. Meaning, I could be going at a velocity of negative 42 kilometers per hour. And that denotes that I'm traveling that fast, but I'm also going either one of two directions, down or to the left. And that's where the negative comes from. Whereas speed, and we might familiarize ourselves with that notation, speed is the absolute value of velocity. So in 2.1, we are asked, how do we measure speed? So what is speed? It is the rate at which we are traveling. It is a rate of change. So here is something that you will be comfortable seeing a lot. S of t. That represents the position of an object. And we'll see different notations, but let's keep going. S of t is the position of an object at a given time. So if we are asked, this is a key word right here, if we're asked what the average velocity is over a closed interval, what the average velocity is, I hope you're seeing it's rate of change, right? So if I have S of t and I want the average velocity over these two x values of a and b, it's S of b, I'm over here, minus S of a, over b minus a. That is, people, y2 minus y1 over x2 minus x1, but we're going to see this written in two different ways. Blue is way 1. Now, let's talk briefly about way 2. And I hope you see in this example, here's my graph of S of t. There's my, my t-axis and my y-axis, S of t. And so my graph looks like so. It's this curve. And I pick these 2 points on that graph. And you'll notice instead of us saying it's these 2 points A and B, where we can just do S of B minus S of A over B minus A, we now say I'm picking this point A, but this point I'm going to refer to as a point that is h units away from A. So h fluctuates from time to time. So if I did that, then I would just refer to this as A plus h. And so its corresponding y value is this, S of A plus h. But we're still taking the rate of change. We're still taking y2 minus y1, and that's why we see here we've got S of A plus h, that's my y2, minus my y1. Now let's look at what the x2 minus x1 does, because now that's A plus h, because that's my x2, minus my x1, which is minus a, and we'll see, or we identify, that's how we're getting this expression when we're referring to these 2 points as A and A plus h. And then at the bottom, we can see how we are expressing what the average velocity of an object is. It is our net change, so it's the change in the y's over the change in the x's. This is not a new concept, folks. It's slope. It's change in y over change in x. But wait, there's more. We are now thinking about, instead of average rate of change, we are now going to introduce this concept of instantaneous. If I want to know the velocity at a specific point, not over the span of hours 1 and 12, right? I want the instantaneous velocity at a given point in time. And so this is where we're going to bring in limits. So instantaneous velocity, as you see, is the number of the average velocity approaches as the intervals decrease in size. What? So all that means is I'm going to take this useful s of a plus h minus s of a all over h, and we're going to let the difference between those 2 points, a and a plus h, get smaller and smaller, right? So we're going to take this rate of change, which is our average rate of change, but then we're going to close that gap so that we then find the instantaneous rate of change. Let's see what that looks like on Desmos. So here, for example, and I can't write on this, but I can at least drag some things. This black point right here represents my A. This red point right here represents this point that is h units from A. So if I want to find the instantaneous rate of change at that black point, what I'm going to do with this red point, A plus H, is I'm going to let that distance between those 2 points get smaller and smaller and smaller until I no longer work with, remember this term, a secant line. I'm going to be working with the slope of the tangent line. So we're just going to close that gap, and we're going to let the distance between A and A plus H get smaller and smaller until we can see what that instantaneous rate of change is. So if we want to come up with our equation for instantaneous velocity at a given point, at a given time, let's say A, then we're going to use the average rate of change, that average velocity, and let the distance between those 2 points shrink and approach 0. So we're going to use that equation that's expressed above. It's our change in position over the change in time, but we'll let our h, the difference between those two, get smaller and smaller. So this equation will give us our instantaneous velocity. And for visual reference, what we see here is a depiction of what that instantaneous velocity would look like at that given point A. The rate of change, if this were my position function, it would be the rate of change right at that point A. So it is that rate at that one point. Whereas average, and I hope this makes sense to you, we think average is over an interval. And that's where we think in terms of slope. That's where we take our S of B minus S of A over B minus A. Average versus instantaneous. So let's look at this example. For question 1, we're asked to find the distance, or we're given that the distance S that a bike has traveled in a race is shown in this table. And we want the average velocity over the interval from t equals 3 to t equals 5. So this is where we're thinking S of 5 minus S of 3 over 5 minus 3. So let's look at those corresponding values. S of 5 is 119, whereas S of 3 is 70, and then 5 minus 3 is 2. Gives us 49 over 2, which cleans up to 24.5, but I'm not finished because I need units. So let's look and see, what are the units for the y values? That's in miles. So we know that this value is in miles. Our x or t is in hours. So this would read miles per hour. Keep that in mind. No units, no credit. So for the second question, we are given this free-falling object and it's dropped from this height of 200 feet. And the height is S of t, t is time. And here is the function that is given. We're going to start doing some graphing calculator work here. So our S is feet, t is seconds. We're asked for, again, average rate of change over the following interval. So from interval 1 to 2, get in the habit We know it's s of 2 minus s of 1 over 2 minus 1. Let's just write these out first, and then we'll figure out the numbers. For interval B, I think we kind of see this pattern, s of 1.5 minus s of 1 over 1.5 minus 1. And then the last one, 1.1, and you'll notice they are intentionally making the difference between the two x's get smaller and smaller. So we're slowly creeping into going from average to instantaneous. So let's see what this looks like on our calculator. All right, so you'll notice here that I have in my y equals, so I'm going to go to y equals, I put that equation in my y1. And the reason I did that is because I need to use it 3 times. So I may as well just keep it in my y equals. So here we're just going to do a little bit of practice by plugging in and making sure we know where some of these shortcuts are. So the one thing I do like to do is I like to go to alpha y equals when I need to type in a fraction. And you'll notice it says right there n over d, numerator over denominator. And that way I don't have to worry about the parentheses. It's already going to be in there. All right, so what's the next thing? I want to do s of 2 minus s of 1. So then I can just call up my y equals, it's right there. And I can put it in just like function notation. I can't see. So y1 of 2 minus alpha trace, call up y1 again, and then over 2 minus 1, 2 minus 1, enter. And that's going to be my first, and I think the units were in feet per second. Now, fun. So if I wanted to just do the second one, I think the second one, folks, I can't remember. I think it was 1.5. So instead I would type in 1, and then I can insert, or you could just do it all over again. I could insert the 0.5, and then go here, type in 1, insert the 0.5, and so there is the second average velocity. And then the last one, I'll just go back to second, enter, and then here I can just replace those with, I think it was 1.1 for the last 1.1. And so we see that it goes from negative 48 feet per second, negative 40 feet per second, negative 33.6 feet per second. And that negative is because it's dropping. All right, so let's work through problem 3. Let's calculate the instantaneous velocity for this function s of t when t is 3. So instantaneous velocity at 3 should look like this. The limit as h approaches 0 of, I'll use s, since that's what the function is, s of 3 plus h minus s of 3 all over h. Let's see what this looks like, folks. So this is our limit as h approaches 0 of 3 plus h squared plus 2 times 3 plus h, and I hope everyone can see, is everywhere there's a t in this function, I replaced it with 3 plus h minus, and now s of 3. So I'm going to put that in parentheses. So 3 squared plus 2 times 3 all over h. Now let's clean up house. So this is going to look like this. The limit as h approaches 0 of, and I'm foiling the 3 plus h, that's 9 plus 6h plus h squared, plus, now I'm going to distribute, I'm onto this part, I'm going to distribute the 2, so that's 6 plus 2h minus, I'm going to distribute the 9, 3 squared gives me 9, 2 times 3 is 6, so minus 6, all over h. Let's see if anything goes. 9s go, 6s go. So that takes us to the limit as h approaches 0 of 6h plus h squared. Oh, plus 2h all over h. I can clean up. H approaches 0 of, that looks like h squared plus 8h all over h. I can factor out an h from the numerator. Why would I do that?
Murray should go out.
Over h. That's why I should do that. And now if we plug that back in, let's see, if I plug in 0 for h, I'm left with 8. And here, because they gave me no units, I can't write the units. So here we're asked in problem 4 to estimate the limit by substituting smaller and smaller values of h. It's another calculator question, and we are asked to round to the nearest thousandths. That's what we're going to do for the rest of our lives together, people. We're rounding to at least 3 decimal places at the very end. So let's see what this looks like on our calculator. So you'll notice in y equals, I have 3 to the h minus 1 over h, and I just have x's in place of my h's, and it asked us to substitute smaller and smaller values of h. So this is what I'm going to do. I'm just going to go to my table set, so I'm going to go to second table set, and I'm going to let my h smaller and smaller values. How about we start our table at 0? But then I want values super duper duper close, but not equal to 0, because that's going to be an error. So how about we do point, I don't know, 1, 2, 3, 4, 0.0001 for our delta table. Those are the increments you might remember. So now, if we go to second table, I'm going to scroll up just a smidgen, and it's asking us to round to at least the nearest thousandths. That's 3 decimal places. Now here's something to take note of. We can either round to the 3rd decimal or we can truncate, meaning you can just look at it and say your answer, and there are 2 acceptable ones, is either 1.098, that's truncated, that means ignoring the 4th one, or 1.099. That's if we round. Both of those answers are acceptable. So for the remaining parts of this, if you just work through these problems, and I stopped it right at that black line, I'll put it in blue right there. The next part is the 2-2. So let's look at question 5 and see if you're comfortable with all of 5, then shut me off. All right, so we're just going to work through some of these. So if we're given a ball tossed into the air from a bridge, and the height is in feet, it's y, above the ground. And so we are given that this function is negative 16t squared plus 50t plus 36. So that's the height, and t is in seconds. Here we go. How high above the ground is the bridge? So pretty much we want to figure out what f of 0 would be, right, before that ball is tossed. And if we look, that looks to be 36 feet. Fine. B asks us, what's the average velocity of that ball for the first second? That's another way of saying, folks, from time t equals 0 to time t equals 1. And so I'm hoping that you put this equation into your y equals, and then from there you evaluate f of b minus f of a over b minus a, f of 1 minus f of 0 over 1 minus 0. And we would get the answer that's on the bottom of that page. So part C is asking us to approximate the velocity of that ball at t equals 1. So this is where I'm going to take that interval that's given, maybe the 0, 1, but I'm going to make it significantly closer to 1. So maybe 1.001, or you might be thinking 0.99 to 1. You pick your poison. Either one is going to work. So, and again, this is going to be an approximation, so it's not going to be 100%. I'm going to try putting this one into my calculator, and I'll show you what that looks like as well. So this is what I'm typing in. So you notice I've got that equation in my y equals. I'm going to quit from there. And then I also have this f of b minus f of a over b minus a. And I'll tell you right now, if I added an extra o in the 1.0001, I would get an even more accurate answer. If I hit enter here, 17.984. So that looks like it's close to 18, or I would accept for this one just because it said approximate, 17.984. I already forgot, like feet, I think it's feet per second. So to find the maximum, you'll notice that I put the equation in my y equals, and then I tinkered a little bit with the window, and I had that as a workable window. We've got some options there, right? So my graph looks a little something like that. This asked us for the max value. So I'm gonna go to second trace, that's calculate, and I'm gonna ask for the maximum, that's number 4. So I'm gonna hit 4, and then it's asking me, what's our left bound? Because I wanna figure out what window do I want the max value at. So I make sure, and I hit enter. I make sure that my tick mark is to the left of that max. And then for the right bound, I want to go to the right of that maximum value. Make sure we pass it. Hit enter, and you'll see the little arrows. Your guess, we don't care, just hit enter. And it's telling us right there that our maximum is at 75.0625 when my x is 1.56 and some change. Here's what's nice is if I quit and I go to the X button, my calculator still remembers that that's the X. So I'm gonna keep that in mind when it's asking me to answer the rest of that question. Because I believe it asked, now what is the average velocity at that maximum value? So let's do that next. So you'll see, since it asked for the average velocity once it hit its peak, then I plugged in y1 of x, because remember the x still kept the 1.5, whatever that was. So I've got y1 of that x minus y1 of 0 over x minus 0. We hit enter, and it is approximately 25 feet per second. And E is our bonus question. We needed E in order to get D. So when did that ball reach its peak? We can pull up that X value and say that was at 1.562 seconds.